Welcome, dear students. In this brief session, we will discuss certain important topics which we have discussed in this particular subject up till now. Okay, so basically, it is a review session in which we will be reviewing the important concepts already discussed up till now. So, I will start with the Chomsky hierarchy. And as per the Chomsky hierarchy, we have four types of languages: type 0, type 1, type 2, and type 3. Okay. So type 0 languages are recursively enumerable languages. We have already discussed what should be the format of the productions in this particular kind of language. Then we have discussed type 1, it is the context sensitive languages, and type 2, these are the context free languages, and type 3, which are the regular languages. And we have also discussed that these four languages have a containment relationship in them. So all the type 3 languages are contained into the type 2 languages. That is, all regular languages are also the context free languages. Similarly, all type 2 languages and type 3 languages are contained inside the type 1 languages, meaning thereby every language which is regular, that will also be context free. Every language which is context free, that will also be context sensitive. And similarly, all the context sensitive languages will be the recursively enumerable as well. Okay, so there is a containment relationship in these four kind of languages. Among these four, we have up till now discussed type 3 and type 2 languages, and we have discussed various tools by which either we can generate these languages or we can test whether a given string is inside that particular language or not. So let us start our discussion with the type 3 languages, which are the regular languages. For the regular languages, we started our discussion with the FAs. Okay, so we have started discussing FAs. We have discussed how we can design FAs. Okay, so we have discussed the design of FAs. We have discussed basically three kinds of FAs, which are DFA, NFA, and epsilon NFA. So DFA is our deterministic finite automaton, NFA is our non-deterministic finite automaton, and epsilon NFA is again the non-deterministic finite automaton, which is also allowing the null moves. Okay, so these are the three differences we have already discussed in detail, how we will design DFAs, NFAs, and epsilon NFAs. We have also discussed at that point of time design of DFAs in case of complex problems may be difficult. So normally what we try to do, we try to design NFAs or the epsilon NFAs. And then we have the conversions. We have the conversions. We can convert our NFAs to the DFAs. We can convert our epsilon NFAs to the NFAs, or directly we can convert them to the DFAs. So we are already having the algorithms for these kind of conversions. So NFA to DFA we can convert. We can extend that conversion to convert epsilon NFAs to the DFAs directly. And we also have the method by which we can remove only the epsilon moves, and from the epsilon NFA we can find an NFA. So these all kind of conversions we have already discussed. Then in FAs as well, we have also discussed the FAs with the output. In the FAs with the output, we have discussed two kinds of FAs, two kinds of machine. These are the Moore machine and the Millet machine. So we have looked at what the Moore machine is and what the Millet machine is, and then we have seen how we can convert a Moore machine into the Millet machine or a Millet machine into the Moore machine. So from the point of view of examination, these kind of conversions are important. Then we have discussed one more concept, that is the regular expression. So we have discussed the design of regular expression, how we can design the regular expressions. And we have also seen that these regular expressions are closely associated with the NFAs. Whenever we look at the regular expression, we can easily convert, or we can easily design it into an NFA. And then that particular NFA we can convert into the DFA. So in this manner, we can convert our regular expressions to the DFAs. There are direct methods also to convert regular expressions to the DFAs. So from the regular expression, using the Kleen's theorem, we can directly convert a regular expression into the corresponding DFA. Basically, this regular expression through this Kleen's theorem is converted into the epsilon NFA, and then we have the method to convert epsilon NFA to the DFA. So we can use that method and we can ultimately convert our regular expression to the DFA. So for converting a regular expression to DFA, we have to first use the Kleen's theorem, and from the regular expression we will convert it to the corresponding epsilon NFA, and then that epsilon NFA will get converted to the DFA. So in this manner we can convert a regular expression to the corresponding DFA. Or another method we have already discussed, because regular expressions are closely associated in their design with the NFAs and epsilon NFAs. So directly also by observing in simple cases we can directly convert our regular expression to the NFAs or epsilon NFAs, and then we can convert it to DFA. We can also do the reverse conversion. Suppose we have an FA with us and we want a regular expression for that. So if we are having a FA, we can use the Arden's theorem and we can convert a given FA to the corresponding regular expression. So this is also important from the point of view of examination. We have discussed that our FAs are the tools by which we can test whether a given string is inside the language or not. So these are basically the testing tools. Now the regular expressions which we have discussed are the generating tools. So if we know the regular expression, then with the help of that regular expression, we can generate words into the given language. So this regular expression is a generating tool, and these FAs are the testing tool. We have one more generating tool, that is the regular grammars. So we have discussed what we mean by grammars, then we have discussed what are the regular grammars. So regular grammars are identified by the type of production, because these represent the type 3, that is the regular languages. So regular grammar have a specific format for its productions. So we have discussed what the regular grammars are, and then we have discussed how these regular grammars we can either directly design or we can convert an FA to the regular grammar, and if we are having a regular grammar, how we can make an FA from it. So we have both kind of tools available with us. So regular grammars are also the generating tools, and if we are having the regular grammar with us, we have the method by which we can convert this regular grammar to the corresponding FA. And suppose if we are having the FA, that is the testing tool, then we can generate the corresponding regular grammar. We have an algorithm for it. So both kind of algorithms we have discussed. Now one important topic in the regular languages was the pumping lemma. So its proof is also important. So revise its proof as well. And this pumping lemma was basically useful to test whether a given language L is regular or not. So basically we were using this pumping lemma to prove that certain given languages are not regular. So we have already discussed the method by which we will be testing whether a given language L is regular or not through the pumping lemma. Then one more important topic was the closure and decision properties of the regular languages. So closure properties are whether a set of regular languages is closed under a given under a given operation or not. Like suppose under the union operation, whether the set of regular languages is closed or not, meaning thereby if two regular languages are given, and if we form another language by making a union of these two languages, so whether that union, the resultant language will also be regular or not. If it is regular in each and every case, then we say that set of regular languages is closed under the union operation. So similarly, there are five, six important operations which we have discussed, over which we have tested that set of regular languages is closed under those operations or not. Then similarly, we were having certain decision properties, certain decision problems. So decision problems are nothing, these are the questions about the language. So to answer that particular question about the language, if we have a well-defined algorithm, then we say that our problem is decidable, otherwise it is undecidable. So there are important questions like whether a given language is empty or not, whether a given string belongs to the language or not, or whether the language is infinite or not. So these kind of certain questions about the languages. So these are the important decision properties of the regular languages. So this was all about our discussion of regular languages. Then one more important topic that was the Myhill-Narode theorem, that also we have discussed. That Myhill-Narode theorem is also useful for testing whether a given language is regular or not, and it can also be used for the minimization of the FAs. So as the FAs are the tools by which we can test whether a particular given language is particular given word is inside the language or outside the language. So design of these FAs are important because these designs are many times realized into the circuitry, into the machines, real world machines. Okay, so our designs need to be optimized. So we have also discussed how to minimize our design. So how to do the optimizations of our design. So minimization of FAs is also an important topic. Then we have discussed our type 2 languages, which are the context-free languages. And in context-free languages, we have discussed the context-free grammars. So these were the generating tools by which we can generate the context-free languages. In this, we have discussed the design of context-free grammars, not CFLs, the context-free grammars and regular grammars. Okay, or we can say design of the grammars for context-free languages and the regular languages. Then we have discussed the ambiguity and its removal. So what do we mean by an ambiguous grammar? So for this, what we do, we try to find the leftmost derivation of a particular word in the as per that particular grammar. If corresponding to any word in the language defined by the grammar, we find more than one leftmost derivation tree, then we say that that particular word is ambiguous. And if a word in a grammar is ambiguous, the whole grammar is said to be ambiguous. So in this manner, we check whether a given grammar is ambiguous or not. And once the grammar is ambiguous, how we can convert an ambiguous grammar to the unambiguous grammar. So we have also discussed their methods. We have seen how we can remove the ambiguity. We have also discussed that for the removal of ambiguity, we need some disambiguating rules. And this removal of ambiguity in each and every case is not possible. So there are the inherently ambiguous languages for which there is no other grammar than the ambiguous grammar is possible. So that's why the ambiguity is inherent in the definition of the language. We have taken that those examples as well. Then we have discussed the simplification of CFG. So the simplification of CFG is nothing but the removal of certain useless things from the grammars and its productions. So in this simplification, we have discussed 4 kinds of simplification. That was removal of all the variables which do not derive a terminal string, or the removal of symbols which do not appear in any centennial form, removal of null productions, and removal of unit productions. So these simplifications help us to optimize the design of our context-free grammars. Then we have discussed normal forms. These normal forms are nothing but these are the restricted forms of the context-free grammar. So these forms are useful for different purposes. So 2 different kind of normal forms we have discussed, that is the CNF Chomsky normal form, GNF the Gribich normal form. And we have discussed that advantage of this CNF is that the shape of the derivation tree is of a binary tree. Okay. And in GNF, we were having the advantage that it was a natural expansion or natural generalization of our regular languages or regular grammar. So that's why all the results related to those can also be applied to the context-free grammars. So these were the advantages of CNF and GNF. Then we have seen how to convert a grammar into the CNF, and then we have seen how to convert a given CFG into the GNF. So this was all we have discussed up till now. Now we will be moving to the new topic, that is the PDA. This PDA is called push down automata. Like FAs are the tools for the regular languages, similarly PDAs are the tools for the context-free languages by which we can test whether a particular given string is part of the language or not. So these are the similar kind of tools as FAs are for the regular language, but these will be for the context-free languages. So in our next lecture, in our next session, we will be discussing these push down automatons. Thank you.